Welcome to the next session, my dear friends. In the previous session we have discussed up to the question number 17. We are continuing it from question number 17. Question number 18. So GATE 2018 1 mark set 1. Question number 18. So there are 20,000 vehicles operating in a city with an average annual travel of 12,000 km per vehicle. The NOx emission is 2 gram per kilometer per vehicle. The total annual release of NOx. Very simple question. So number of vehicles. So these many vehicles are operating in a city. An average annual travel is equal to 12,000 km per vehicle. Okay. So each kilometer traveling evolves 2 gram per kilometer NOx. So NOx emission 2 gram per kilometer travel. Okay. Per vehicle. So what is the total amount of NOx released in kg? So total very simple question. So 2 gram per kilometer per vehicle multiplied by how many vehicles are there? 20,000 vehicles are there. And each vehicle travels how many kilometer? So 12,000 kilometer. Okay. So this is nothing but the answer to 20,000, 12,000. So if you multiply these three, we will get it as 24 into 10 to the power of, we will get this as 48 into 10 to the power of 7 grams. So 2 into 12 to the 24 to the 48 into 4 zeros and 3 zeros, 10 to the power of 7 gram. So if I want it in kg, then 10 to the power of 3, divide it with 10 to the power of 3, that is 48 into 10 to the power of 4 kg. So that means 4,80,000 kg. It is 4,80,000 kg. That is the answer. So next question. GATE 2007 2 marks. Question number 19. Two electrostatic precipitators are in series. The fractional efficiencies of the upstream and downstream electrostatic precipitators of a size dP are 80% and 65%. What is the overall efficiency? See, whenever we are having the electrostatic precipitators in series, then the overall efficiency is equal to efficiency of the first electrostatic precipitator, so that is N1. So this is the efficiency of the first precipitator, plus 1 minus N1 into N2. So this is the actually overall efficiency when the electrostatic precipitators are kept in series, when ESPs are because so whatever the first one ESP will be there, Into that we are sending this pollutant air. So there some pollutant is removed, and then the rest. So in this 100%, N1 is removed. So that N1 removed portion, that is 1 minus N1 portion, in that N2 is removed. Are you getting the point? This is the overall efficiency. This is the efficiency of the first ESP. From the 100%, some 80% here. What is the given data? Given data is this N1 is 80%. So the first ESP is having an efficiency of 80%, and the second ESP is having an efficiency of, downstream ESP having an efficiency of 65%. So already in 100%, 80% is removed. In the 20%, 65% is removed. So that is the overall efficiency of the removal. Okay. So 80% plus 0.2 into 65%. So this is the overall efficiency of the ESP, that is nothing but 0.93 or 93%. Okay. It is again a simple question if you know the formula. Otherwise, it is a very tough question. So, GATE 2009. GATE 2009, 1 mark, question number 20. Question number 20. Particulate matter, fly ash, carried in the effluent gases from the furnaces burning fossil fuels are better removed by, obviously, fabric filter is a better removal, efficiency is more. After fabric filter, it is electrostatic precipitator. I already told you, we use this electrostatic precipitator in thermal power plants and different kinds of furnaces where we are getting the ash, where we are getting the particulate matter. There we install the electrostatic precipitators to remove them. Okay, so that is why from the options given, electrostatic precipitator is the solution because it is having the highest efficiency from the options given, and it is also used in industrial purposes. Okay, the answer is ESP. The answer is ESP for the question number 20. So GATE 2014, question number 21. GATE 2014, 1 mark. GATE 2014, 1 mark, set 2, question number 21. Majority of the questions from this topic are of 1 mark. Very small questions are coming. So very easily you can solve. The two air pollutants control devices that are usually used to remove very fine particles from the fuel gas. So the most fine material can be removed using the two control devices that are electrostatic precipitators and fabric filters. If you look at the options, then cyclone and venturi scrubber can only remove the larger materials where the surface area is more. So these are all wet control devices. Wet control devices can remove larger particles up to 2 micrometer and all. But if the particle size is even less than 1 micrometer, also fabric filter can remove. So that is a very fine particles can be removed by fabric filter, that is for sure. So all these scrubbers and all, they can remove only larger diameter particles. So very fine particles can be removed in electrostatic precipitator and fabric filter. That is the answer. Excuse me. So next is question number 22. Question number 22. GATE 2016, 1 mark, set 1. GATE 2016. 1 mark, set 1. It was decided to consider a fabric filter using the bags 0.45 meter diameter and 7.5 meter long for removing industrial stack gas containing particulates. The expected rate of airflow into the filter is 10 meter cube per second. If the filtering velocity edge 2 meter per minute, the minimum number of bags rounded to the nearest higher integer required for continuous cleaning operation. So let us extract the data first. So what is the given data? Given data is the diameter of the filter 0.45 meter. This is the diameter of the filter, and the length of the fabric filter. Length of filter is 7.5 meter. That is the length of the filter. So the airflow rate 10 meter cube per minute. Airflow rate 10 meter cube per second, and velocity of the filter 2 meter per minute. Okay, 2 meter per minute. So number of bags required. See, generally the fabric filters. So this is how the fabric filter will look. So the gas will go out and it will be filtered through the periphery. It will be filtered through the periphery of the fabric filter. So, and this velocity is given as 2 meter per minute. So what is the velocity of the air movement through the fabric filter? That is given as 2 meter per minute. So it happens around the periphery surface of this fabric filter. So that is why, so here he is asking he has given how many number of filters are required. So we can find the surface area of each filter. So this is a similar kind of filter problem which we did in our water supply and wastewater engineering also. So filter will be done along the surface. So you can get the surface area. So this is the velocity and this is the discharge. We can also call this is the rate of flow, and this is the velocity of flow, and this is the rate of flow. So if you divide it, you will get the surface area. The total surface area required. Total surface area required is nothing but Q by V. That will give us total surface area. So Q is equal to 10 meter cube per second by 2 meter per minute. Convert this into seconds. 2 meter by 60 minutes, 60 seconds. So it will become 60 meter per second. So it is 300 meter square. So the total surface area of the fabric filter needed is 300 meter square. This is the total area of the fabric filter needed. So each fabric filter surface area is pi into d, diameter into height, length, pi dh, because it is in cylindrical manner. So the surface area will be taken as pi dh. Okay. So which is pi into d. What is the diameter? 0.45 and the length is 7.5. So this is the diameter. This is the area, surface area of each filter. So what is the value of that surface area? Surface area of each filter will be coming around. So no need of calculating this. This is the surface area of individual. So number of filters. Needed 300 meter square. This is also meter square by pi 0.45 into 7.5 meter square. So this will be the answer. We are getting this ratio as 28.29. 28.29. If you round it off, it will become 29. So 29 number of fabric filters are needed. 29 number of fabric filters are needed to take care of the given rate of flow with a given rate of velocity. So that is the question number 22. So let us go to the next question, question number 23. Question number 23, GATE 2016, 2 marks, set 1. GATE 2016, 2 mark, set 1. Question number 23. So the question is like this: an electrostatic precipitator ESP with 5600 meter square of collector plate area. Collector plate area is 96% efficient in treating 185 meter cube per second of fuel gas from 200 megawatt thermal power plant. It was found that in order to achieve 97% efficiency, the collector plate area should be 6100 meter square. In order to increase the efficiency to 99%, the ESP collector plate area should be how much? See, in electrostatic precipitator, what is the given data? First of all, let us extract the given data. What is the given data? So electrostatic precipitator efficiency is 96%. So the rate of flow, okay, so rate of air flow, (185 meter cube per second). So this is the rate of air flow, okay, and efficiency 96% when the area of the plate is 5600 meter square. 5600 meter square, and efficiency has grown to 97% when this A2 has become 6100 meter square. So when you increase the area of the collecting plate, when you increase the area of the collector plate to 6100 meter square, it has increased it to 97%. So when I want an efficiency of 99%, what is the A3 value? This is the question. So what is the efficiency of the electrostatic precipitator, which we have discussed in the previous sessions? The efficiency of the electrostatic precipitator is 1 minus e to the power of AW by Q, 1 minus e to the power of minus AW by Q. So what is the A here? A is collector plate area, okay, and W is velocity, wind velocity, and Q is air flow rate, okay. So if you take the efficiency as 96%, so 0.96 is equal to 1 minus e to the power of the collector plate area is 5600 meter square into wind velocity I don't know, and 185 meter cube per second is the, so this is the Q. So from solving this, we will get the wind velocity. So we will get the wind velocity as 0.1063 meter per second, 0.1063 meter per second. So after getting this, simply take this efficiency as 0.99 is equal to 1 minus e to the power of minus A is I don't know, and the wind speed is 0.1063 meter per second by this 185. So if you solve this equation, If you solve this equation, then we will get the value of area. Then we will get the value of area. We are getting the area is 8012.39 meters square, approximately 8012.39 meters square. So this is the area required to have an efficiency of 99%. That is question number 23. So let us go to the next question, question number 24, GATE 2019. Next question is GATE 2019. 2 marks, set 1. Question number 24. A sampler of air is analyzed at 0 degrees 1 and 1 atmospheric pressure is reported to contain 0.02 ppm of NO2. Assume the gram molecular mass of NO2 is 46 and its volume at 0 degrees centigrade 1 atmospheric pressure is 22.4 liters per mole. So the equivalent NO2 concentration in microgram per meter cube. So very simple question. So he is asking that he has given the units of NO2 in microgram in ppm. He want it to convert it into microgram per meter cube. So that is the question here. So what is the given data? So NO2's concentration is 0.02 ppm at 0 degrees centigrade and 1 atmospheric pressure. This is the ideal condition. That is nothing but standard temperature and pressure. So he has given it at standard temperature and pressure. And at the same standard temperature and pressure, he is asking it in microgram per meter cube. He is asking in microgram per meter cube. So what is the conversion of ppm and microgram per meter cube? So 1 microgram per meter cube is equal to 1 microgram per meter cube is equal to 22.4 by m into 10 to the power of 3 or 1 ppm is equal to m into 10 to the power of 3 . So this is 1 ppm. If 0.02 ppm is there, then here also m into 0.02 into 10 to the power of 3 by. So what is the m value? M value was given for NO2. So NO2's molecular weight was given as 46. It is 46. So the answer should be equal to 46 0.02 into 10 to the power of 3 by 22.4 microgram per meter cube. This is the answer. Okay. So by solving this, (46 into 0.02 into 10 to the power of 3 so 410.714. Microgram per meter cube is the answer. Sorry, this should be 10 to the power of minus 3, if it is going this side, 1 ppm is equal to m into 10 to the power of, small correction, I think so. Yeah, it is correct, 10 to the power of 3 only. I have made a calculation mistake. This is not for 410.714. It is 41.0714. So there is a calculation mistake. Okay, that is 41.0714. So 2 decimal places, then it will be 41.07. That will be 41.07 is the answer. Okay. So next question. Question number 25. 2006 2 marks question. GATE 2006. GATE 2006. Question number 25. The mean indoor airborne chloroform CHCl3 concentration in the room was determined to be 0.4 microgram per meter cube. Use the following data. T is equal to 293 Kelvin and P is equal to 1 atmosphere and R is equal to 82.05 into 10 to the power of minus 6 atmosphere per meter cube, like that. So atomic weights are given. So this concentration should be expressed in parts per billion on volume basis. ppBV is equal to, okay. So now here what is the given data? It is also unit conversion only. So very simple question. So given data is that, so the concentration of CHCl3, okay, chloroform is equal to microgram per meter cube, okay. And T was given as at and P is equal to 1 atmospheric pressure, and R is equal to 82.05 into 10 to the power of minus 6 mole meter cube per atmospheric pressure and degree centigrade. Okay, so this is degree centigrade is not there, it is Kelvin. Okay, so this is what is given. So now convert this into ppBV. So what is the concentration CHCl3 in ppBV? That is volume basis, means what? 1 ppBV is equal to, so 1 meter cube of any gas by billion, that is 10 to the power of 9 meter cube of air. So this is the volumetric basis. So this is called ppBV. Okay, this is called ppBV. Now I told you already during the explanation of this conversion of the units. Okay, so 1 ppB is equal to 1 ppB is equal to, if the constant is different, then 1 ppB at any temperature, T and P, it will be equal to m by 22.4 microgram per meter cube. M by constant, m by similarly 1 microgram per meter cube is equal to constant by m ppB V at any. So what is this constant? Also I have told you, constant is nothing but what? So if you take PV is equal to nRT, that is RT for 1 mole. So the constant is nothing but, so R by, so the volume RT by P. So this is nothing but the constant RT by P. What is R? R is 82.05 into 10 to the power of minus 6, and T is 293, and P is 1. So it is 1 only. So if you multiply this, we will get the constant. You multiply this, we will get the constant. So what is the constant value we will get? Okay, here constant value, we need to multiply it like this. I have given the formula for the constant, that is 0.08205, 0. into T by P. This is what is the formula I have given for you for finding the constant. So 0.08205 into 293 by 1. If you do, you will get the constant. You will get the constant. Okay. The constant will be 24.04. 24.04. Or else we can do it in other way also. It is 22.4 for, it is 22.4 for 273. Okay. It is 22.4 for 273. When you increase the temperature, volume will increase. Okay. So that means 22.4 into 293 divided by 273. So by this way also you can find, but the pressure should be constant. Pressure should be constant. If pressure is constant, we can get this volume. Actually, we will get it as 24.04 meter cube. Okay, this is the constant value, 24.04. The same thing we can get in from other way also. From other way also, if the pressure is same. So 273 at 273 Kelvin. At 273 Kelvin, it is 22.4 liter. Okay, and if it is 293, so for 1 Kelvin, it is 22.4 by 273. So for 293 Kelvin, it is 22.4 into 293 by 273. So by doing that also we will get 24.04 only. But the thing is, for establishing this comparison, the pressure should be equal to 1 atmospheric pressure. So otherwise we cannot do this. When the pressure is given 1 atmospheric pressure, then doing this lengthy thing, we can simply take this formula also into consideration. We can get this constant. So once you get the constant, so 1 microgram per meter cube is equal to 24.04 by molecular weight. So we need to find the molecular weight of this CHCl3 also. So what is the molecular weight of CHCl3? The molecular weight is, so here carbon 12, hydrogen 1 and chlorine Cl3, 35.5 into 3, 35.5 into 3. So this is the molecular weight. So take this as a denominator, 24.04 into this molecular weight, 12 plus 1. So this is ppBV. So this is for 1 microgram. This is for 1 microgram. 1 microgram per meter cube is equal to 24.04 by 35.5 into 3 plus 1 plus 12. This is ppb. So if you want it for 0.04, here it is 0.4. We want it for 0.4 microgram per meter cube. Then multiply here also. Zero point 0.4, we need to multiply here also. 0.4 by 12 plus Solve this, you will get the answer. If you solve it, you will get the answer. So let us see. 24.04 into 0.4 divided by 12 plus 1 plus 35.5 into 3. So that is 0.08. Okay, that is equal to 0.08 ppbv. Okay, that is the answer. Question number 25 is over. So let us go to the next question. Question number 26. This is also unit conversion. Question number 26, 2015. So 2015, two marks set 1. Question number 26. The concentration of sulfur dioxide in ambient temperature was measured as 30 microgram per meter cube. Under the same conditions, the above SO2 concentration expressed in ppm. So very simple question. It is a very simple question. So it was given that, what is the given data? So the SO2 concentration of SO2 is 30 microgram per meter cube. 30 microgram per meter cube. Then what is the concentration in ppm? So what is the conversion? 1 microgram per meter cube. 1 microgram per meter cube is equal to 22.4 by m into so at standard temperature and pressure. So it was given at ambient temperature and pressure, means it is standard temperature and pressure only. Okay, ambient temperature and pressure was not given. So we can assume that given P by RT is 41.6 mole per meter cube. So RT by, so P is equal to nRT. P is equal to PV is equal to nRT. So V is equal to RT by P. So this was given as 1 by 41.6. 1 by 41.6 mole per meter cube. So what is the value of this volume? So meter cube per mole. So this is coming around 24.03. So this is coming around 24.03, not 22.4. So that means we need to take the constant as 24.03. So we need to take the constant as 24.03. So instead of 22.4, take 24.03. So this is for 1 microgram per meter cube, 24.03, and the molecular weight of SO2. Sulfur is 32, oxygen is 32, that is 64. 64 into 10 to the power of 3 ppm. So if it is 30 microgram, so for 1 microgram per meter cube, this is the value. For 30 microgram per meter cube, for 30 microgram per meter cube, it is 24.03 into 30 by 64 into 10 to the power of 3 ppm. This should be the answer. Let us verify it. Let us check. 24.03 into 30 divided by 64 divided by 0.011 should be the answer. Yeah, 0.011 is the answer. 0.01146. So this is the answer. Okay, this is the answer. Here see, they have given us the value of P by RT. P by RT is given as 41 point something, 41.6. 41.6 mole per meter cube. Mole per meter cube. So whatever the V value is, nothing but RT by P. That means we need to inverse it. 1 by 41.6, that is meter cube per mole. So it is coming around 24.03 into 10 to the power of minus 3 meter cube per mole. So convert this into liter. So that is 24.03 liter. So this is our constant. Actually, this is our constant. We take it in liters. So whenever we get the volume, convert that volume into liters and take that as constant. Okay. So if you take that, we will get the answer. Very simple. M is the molecular weight. So SO2's molecular weight is 64. Okay. So that is question number 26. So let us go. These are the questions from air pollution. These are the questions from air pollution. So now we are entering into the noise pollution. We are entering into the noise pollution. So we will do one thing. Actually, there are 7 questions are there from noise pollution. What we will do is we will solve these noise pollution questions in the next session. Thank you so much.